let me come back and emphasize something that I've said now numerous times, and that is this whole story is all about capturing electrons and taking energy away from the electrons. So here was our first electron pair. It went from cytochrome B to cytochrome C to cytochrome A3. Here comes the second pair of electrons. It goes to cytochrome B and cytochrome C. Can the second pair of electrons go to cytochrome A3? And the answer is no. Why? Because cytochrome A3 is reduced. We've got to somehow oxidize cytochrome A3 if we want a second pair of electrons to become bound here. Cytochrome C is reduced, cytochrome B is reduced, and now what happens to the movement of electrons? Does the movement of electrons continue? No. What ensures the movement of electrons are oxidation reduction reactions. And if cytochrome A3 has a pair of electrons attached to it, then it's reduced. And no more electrons can flow through the electron transport chain. Unless there's one critical molecule available. And that molecule is oxygen. What's the rule? What does rule number 8 say? Oxygen is the final electron acceptor. So watch what happens. Here comes molecular oxygen. I don't know, I think these stories are absolutely cool. They're amazing stories. And they come back to things we've talked about before. Where is oxygen on this periodic table? It's over here in group 6. It's out to the far right. It is an electron hog. You could say it more technically. You could say it has a very high electronegativity. That means it has a very strong attraction for electrons. And so oxygen comes along and it captures or takes the 2 electrons away from cytochrome A3. And here's the chemical reaction. You guys have all seen this. 2 protons plus 2 electrons plus 1/2 molecular oxygen reacts to form what? H2O. Now watch, everybody come on up here, all eyes up here. So now oxygen's come along and it's captured these 2 electrons that were bound to cytochrome A3. You're going to tell me that cytochrome A3 now is in a reduced or oxidized state? Oxidized. And now the second electron pair can move to cytochrome A3. The third pair of electrons, which was bound to cytochrome B, can now move to cytochrome C. Another molecule of NAD in its reduced state can transfer its electrons to cytochrome B. Here comes another molecule of oxygen, which removes electrons from cytochrome A3, now oxidizing cytochrome A3. This pair of electrons moves here, and as long as this is happening, we are building and maintaining a proton gradient. That proton gradient is the key to the story. It's the movement of electrons through the electron transport chain that's responsible for building a proton gradient. Have we made any ATP yet? No, we haven't. So how does that happen? Well, as I mentioned, if we can make pumps run backwards, we can make ATP. So here's a pump, and this is a proton pump or a hydrogen ATPase pump. Jacob Hill.
Yep.
If I have protons moving from an area of high concentration to a low concentration, what's happening to the energy stored in that hydrogen ion concentration? Now, I called his name, but I'm really asking all of you. All of you have to be able to answer this question. If hydrogen ions, if protons are moving from an area of high concentration to low concentration, what's happening to the energy stored in this proton concentration gradient? Jacob.
It has to be transferred to make heat.
What's happening to the energy level? Is it going up? Is it going down? Or is it staying the same?
It's going down.
It's going down. So now we're back to what famous law of thermodynamics? Oh, hurt me. First law of thermodynamics says energy can be neither created nor destroyed. It's simply transferred from one form to another. Who's ready to do some battle? Anybody ready for some test questions? Don't be a bunch of wusses. Come on. Bunch of wimps. Oh my Lord.
That's it.
Miss Tracy, you weren't here last week, so I'm not going to ask you. Were you here? You weren't here on Wednesday, were you? Lucky for you. You ready to go?
Sure.
All right. Here's a test question. How many total electrons are captured due to oxidation reduction reactions?
6.
6?
I don't know. I'm just guessing.
Anybody got the answer? How many total electrons?
20.
20? Well, let's sit there and think about it. How many did we capture in glycolysis? 4. The conversion of pyruvate into acetyl coenzyme A is 4. That's 8. Then we have the oxidation reduction reactions in the Krebs cycle involving NAD. How many electrons do we capture there in a high energy state? 12. So now 20. And then we have 2 molecules of FAD that become reduced, and they capture another 4, right? So how many electrons total do we capture? 24. Here's the chemical reaction. So if we're driving this pump backwards, then that pump has to be making ATP. We have 32 molecules of ADP plus 32 molecules of phosphate that react to form 32 molecules of ATP. So if we're doing some bookkeeping, just give me one moment. Okay, let's see here. Jocelyn, Ms. Gonzalez. So we're doing some bookkeeping. What's the net number of ATP molecules produced as a result of glycolysis?
4.
Let me ask you that question again. What's the net? Do you know what a net is? If I pay you $200 for work, but it costs you $20 to drive to work, what's your net profit for that day? Net. Guys, what are you going to do? What are you tell me? What's the net for ATP from glycolysis? 2 molecules of ATP. Ms. Jocelyn, what's the total amount of ATP produced by glycolysis?
4.
That's correct. It would be 4. Krebs cycle. Mona, what's your answer? Good. Good job. 2 molecules of ATP. Now here's a tough one. Let's see if you guys can get this. Miss Lily, how many molecules of ATP are produced as a result of electron transport chain?
32.
Oh, very good. So you guys will tell me that the net number of molecules of ATP produced are 36 molecules of ATP. Where do we get the biggest bang for our buck? What is the most important set of biochemical events that produces the most ATP? Is it glycolysis, is it the Krebs cycle, or is it electron transport chain? The answer should be very, very obvious to all of you. Where do we produce CO2? I'm curious about that because I know that the air that I breathe into my lungs has very little CO2, and yet the air that comes out of my lungs is very rich in CO2. Krebs cycle, how many molecules? 6. Which is your answer?
4.
That's correct. But there's a total of 6. So where are the other 2 coming from? Pyruvate 2-acetylcoenzyme A.